on exponential functions. So we're going to start off by just talking about normal power functions. These are functions that we've been working with already that are polynomials. And you can see here it is f of x equals x to the fifth right here, where we have x as our base, and we have a number in the exponent. The number in this one is 5, so x to the fifth. And it gives us something like this if we graph it, where we have going towards negative infinity on that side, positive infinity on that side. We have maximum of 5 real zeros. And we know how to find those. In this case, all 5 of them would be at 0. It would be 0, and that's supposed to be 5. We're going to transition into exponential functions. So exponential functions look a lot like this thing on the right, and they are represented by f of x, still a function, equals a, where a is our base, and a is just some number. It's just a mathematical constant. It really can be any number we want it to be, as long as it is greater than 0. So a is greater than 0, and a cannot be 1. If a is 1, we'll look at that in just a second. But x is our exponent. Okay. These look significantly different. So we have this graph here. It looks like it goes off to infinity in this direction, and then it looks like it approaches 0, almost like there's a horizontal asymptote right at that x-axis. The point right here that is significant, where it crosses the y-axis, our y-intercept, is 0, 1. It's going to do that unless we translate it up or down. It's always going to cross at that point, 0, 1. So let's see what happens if a equals 1. So let me just make a quick little table. I'm going to say, right, f of x equals, let's say 1 to the x. So it's f of x. So I get 1 right there. Oh, I guess I can start off with, like, we'll say it's like -2, -1, 0, 1, 2. So 1 to the -2 is still just 1. 1 to the -1 is still 1. 1 to the 0, or anything to the 0 is 1. And I get 1 to the 1 is 1. And 1 to the 2 is still just 1. So in fact, if a equals 1, it just gives us this nice little horizontal line. It is not an exponential function. It's just a linear function of y equals 1. And that's because 1 to any power is still just going to be 1. So other than 1 and all of the positive numbers for a, this is what it's going to look like. We'll talk a little bit about what happens if a is less than 0 in just a little bit. Let's move on a little bit for now. So we can actually use a calculator, and we're going to do that right now, to evaluate these functions, these exponential for certain values. So for f of x equals 2 to the x, for x equals -3.1, that's the same as f of -3.1 equals 2 to the negative 3.1 power. So we're going to go ahead and plug these into our calculator. I'll invite you to do that with me. I'm going to click out here. I will say 2 to the, and I'm going to say negative 3.1. Hit enter, and it gives me 0.116629. For this unit, we are going to be dealing with a lot of very small changes and some decimals. So let's go ahead and round that to the third decimal place, or the thousandths place. So we'll get 0.117. So f of negative 3.1 is approximately 0.117. Now it's not equals because we actually did round it. So it is, well, it's not like, some people may say it's semantics, but it is important to distinguish that f of negative 3.1 does not equal 0.117, it is just approximately. So we'll do the same for our next one. F of, looks like we're replacing x with pi. So we get 2 to the negative pi. And just go to our calculator. Say 2 to the negative pi. I hit enter. Obviously, pi is irrational. It doesn't want to give me a decimal. Typically, your calculators won't. So in this calculator, I am going to actually have to convert it to a decimal. So that's what I'm going to do to be able to get that value. And I get 0.113. So f of pi is approximately 0.113. Okay, so I go on to the next one. F of x equals 0.6 to the negative x. So I say f of 2/3 equals 0.6 to the negative 2/3. So we have that negative. So just when we're typing it into our calculator, so say 0.6 to the, let's do some parentheses here, negative 2 divide 3. So we would just make sure that all of that stays up in the numerator like it should. Hit enter. And I get 1.0 or 1.406 if I read it. So f of 2/3 is approximately 1.406. Okay. Moving on to the last one here, get f of 12, and that equals 1.05 to the 2 times 12. So really we can simplify that and say f of 12 equals 1.05 to the 24. Okay, 1.05 to the 24. I hit enter, and I get 3.225. Okay, so finding indicated values of x given an exponential function, not that big a deal, just plugging things in. We've had quite a bit of practice with that. So exponential functions. Let's kind of look at these graphs, compare them a little bit. I'll make a quick table so we can actually graph some. So let's compare what happens when we have a to the positive x, that's the one on the left side, right? one on the left side right here. And if we have f of x equals a to the negative x on this right side. All right, so let's start off by assigning a value for a. Now remember, a can be any number greater than, we're going to look at numbers greater than 0, and we just don't want to choose 1, because if we choose 1, it's just a linear function, and you don't really want to explore that. We already know lots about linear functions, so let's go ahead and look at our exponential. I went ahead and chose 2 for a. Keep it small, keep it simple. So we're going to look at f of x equals 2x over in the blue, and f of x equals 2 to the negative x. So I'm just going to choose a few values. I'll just go from -2 to +2, and I will do the same values. We get a nice clear comparison on the negative side. All right, so we get 2 to the -2, 2 to the -1, 2 to the 0, 2 to the 1, and 2 to the 2. 2 to the -2 is the same as 1 over 2 to the +2, which is 1 over 4. 2 to the -1 is 1 over 2 to the +1, which is just 1 over 2. 2 to the 0 is 1. Anything to the 0 is 1. Let's see, 2 to the 1 is just that same thing, is 2. And 2 to the 2 is 4. All right, so let's go ahead and graph these. I didn't put any lines on here. Maybe I should do that. 1, 2. Try to make them spaced properly. That's pretty good. All right, so -2, we're down here at 1/4, so somewhere right about there. -1, we're just above that at 1/2. At 0, we are at 1. At 1, we are then at 2, and at 2, we are up at 4. You can see our graph starting to take shape. Let's go ahead and just graph that. Easy. And it goes onward further this way and goes that way. So these graphs do look very similar to our rational functions, or at least half of our rational functions that we were graphing last student. Let's go over to our negative and see what happens there. So this time we have 2 to the -2, which is really just 2 to the +2. We get 2 to the -1, which is 2 to the 1, or 2. 2 to the -0 is still just 2 to the 0. Is 1. 2 to the -1 is 1 over 2, and 2 to the -2 is the same as 1 over 4. So I'll go ahead and draw my graph in here. 2, 3, 4. All right, so at -2, I am all the way up here at 4. At -1, I am at +2. When x is 0, I'm at +1. When x is 1, my value is at 1/2. And when x is 2, my value is then at 1/4. Okay, so I'll go ahead and fix that a little bit. Nice graph there going on forever that way. So you can see they are just kind of reflections one of the other, but you'll notice that specifically that this y-intercept, they both cross the x-axis there at 1, or the y-axis, excuse me, at 1. And that's because when we plug in 0, when it crosses the y-axis, that's when x is 0. In both these, right? Anything to the 0 is 1. So that's why you keep seeing that y-intercept of 1, because anything to the 0 power is 1. So let's talk about our domains for both of these functions. Domain, remember, is the set of all possible x values. And since we have arrows going in both directions, there's no vertical asymptotes here to break it up, or no holes in my function. My domain is just negative infinity to positive infinity. I look at the negative side and same thing, goes forever in both directions. Now the end behavior is slightly different on these two, but it does ring true that the domain is negative infinity to positive infinity for both of these. The range, we looked at the y values for both of these, and if you can see here, they both approach kind of this x-axis, right? They are both approaching the x-axis. Now on different sides, right? This one's kind of on the negative side right here. This one approaches it on the positive side. But regardless, they're both approaching that x-axis, which is y equals 0. So our nice little range here is going to be from 0 to infinity. Now remember, the ranges, these aren't x comma y. This is y comma y when we're talking about. This is an interval on the y kind of spectrum, the y values, possible y values that can go in. So don't confuse it with like an ordered pair. The range on this one happens to be the same, 0 to infinity. All right, so the only things we have left are increasing and decreasing. So f of x a to the x, a to the positive x, on the left side is increasing. Remember, when we're talking about increasing or decreasing, we start on this negative side and we read to the right. So we follow our line, in this case, and we'll start right here. And it looks like it's going up the whole time. Right, there are no changes from increasing to decreasing, so no maximums or mins. It is increasing the entire time. There's no hills or valleys. Right? It's just one getting steeper and steeper. So we're going to say this is increasing from the interval of negative infinity to positive infinity. Now we look at the other one. Let's look at our other graph, and it looks like it is, we start on the left side right here. We go this way, so we follow our graph. And the whole time I'm going down, I'm getting closer and closer to 0 as I go. So that is actually not increasing. Okay? It is actually decreasing. And that is from, let's see, negative infinity to positive infinity. Excuse my little notes right here, they get a little squished, but it reads the same. So they're both increasing or decreasing on the entire interval of our graph. The a to the positive x, or our exponential with a positive exponent, is increasing the entire time. If we have that negative exponent, it is decreasing the entire time. So that's just a little bit about graphs of exponential functions. That will be helpful while you're trying to work on some of those assignments. Let's talk about something special. This is called the natural exponential function. And the natural exponential function looks like this. F of x equals e to the x. Now, e in this case is our base. X is our exponent. So if you don't know what E is, E is just a mathematical, let's see, it is a constant, okay? It is not a variable, okay? So this E is a constant, it's a number. It is an irrational number, okay? Much like pi, is irrational, meaning the decimal that we have for it goes on and on forever and ever, right? It doesn't repeat itself, and it's just a random string of numbers that goes on forever. This E was actually coined by a Swiss mathematician named Leonard Euler. That's spelled Euler. That's Euler. And he lived in the 1700s. He was the one that coined it as E, most likely, I would assume. I'm not me just making a guess, but I'm assuming because he called it Euler's number, which is kind of, a little bit selfish of him, especially considering that this constant, this number, was discovered in the, I believe to be the early 1600s. So, he came in 100 years later and just said, hey, look, I'm going to actually name this, give it a name. And he chose to call it E. So that's where it's from. And what it does, so this number E, it occurs, we'll say it occurs naturally in any situation where a quantity increases. Okay, we can actually talk about kind of a decrease as well. At a rate proportional to its value. Okay, so specifically something is increasing at a rate at proportional to its value. Say something it is doubling, so it's doubling its value every so often, or every interval. And specifically, what this means is it is increasing at a rate continuously. And so E is kind of an interesting one. It occurs in nature, and we see it pop up all over the place. We use it a lot, and we will use it a lot in specifically problems of exponential growth and decay. Okay, those are huge ones that we use it for. We'll use it in what are called natural logarithms. That word natural means that it occurs naturally. It's a compounding, it's the proportion or the quantity increases at a rate proportional to its value very naturally. And so you'll see that a lot in population growth and compounding interest. And that's another one that we'll talk about is interest, so financial stuff. So compounding interest. We use it in calculus with derivatives. Okay. We'll use it again in calculus and maybe in this class, sequences and series. Okay. And then we use it to help us find complex roots. Okay, that's something we'll look at a little bit later in the semester with something called de Moivre's theorem. Okay, so lots of uses, and this by no means is an exhaustive list of all the uses of E, but it is one of those kind of less talked about numbers, especially in up to this point in math. But I'd say it's as influential, every bit as influential as our pi or the number 0. These are big numbers. So E, you'll find, is one that pops up over and over again. Okay, value of the number E. I'm not going to dive into this. I'll post a video how that's actually calculated. If you want to go through, here are the steps on this slide. You want to go through and figure out kind of why it does that, or the ins and outs of getting the number, you can. But bottom line, E is approximately 2.718. That's kind of what we'll use in this class if you are going to round it. I'd prefer you didn't round it, but if you do, use that value, 2.718. And yeah, I invite you to go watch that video on how it's found, but by no means am I going to force you to do that. So this last slide right here, well, second to last, I guess, is just using a calculator to evaluate f of x equals e to the x. Okay. And so we have the first one, f of -2. So what that looks like is e to the -2. We're replacing that x and e to the x with -2. Okay, this next one, e to the 0.25, or to the 1/4, e to the -0.4, and e to the 3/8. Now this is as simple as plugging it into your calculator, so let's go ahead and do that. The first one was E, so on my calculator, it's that button where it has E and then a little box. Yours, if you have a TI-84 Plus, why don't I just show you? Got mine right here too. Okay, so here's my calculator powered on. The E to the X button is this one right here. It's in blue, so that means we have to hit the second key if we want it to show up, second, and then the E to the X. We click that, and you can see we have E and then a little box up there. That's where our we're going to type in this case, -2, look just like that, and it will give you the value. In my calculator, though, so e to the -2, we get, and again, look, my calculator wants it to be it wants to leave it as the irrational number because that's the exact value. But I want it to be a decimal because we're trying to find the decimal values here, an approximation. So I get 0.135, approximately 0.135. Okay, e to the 0.25, hit enter. This time it did give me the decimal. That's interesting. I wonder if it's the negative that did it. 1.284. So 1.284. E to the -0.4. Let's see what happens here. -0.4. Hit enter. Looks like it's 0.670. Approximately 0.670. And e to the, I'm going to use parentheses here because we're doing a fraction. 3 divide 8, I want to make sure that whole fraction gets in the exponent. So x to the 3/8, or e to the 3/8, I mean. And this one looks like I'm going to have to convert it to a decimal. And I get 1.455, approximately 1.455. And that's it. So computing these, Plugging values in and solving it is just a number. So we're just taking some number about 2.718 and raising it to these powers indicated. Okay, so it will give us a value each time. Um, so let's just look at the graph of this, and I already made a table and graphed it. But this is the graph of the function e to the x. So you can see when x is -2, my y value is just 0.135. That's actually a value that we found on this last one, 0.135 right there. Okay, and the dot is right there. And then they get bigger and bigger, as you would say, exponentially, right? The numbers increase from one to the next exponentially. And what the rate of that exponential increase is our natural number. That's e. So it's increasing at a rate of times 2.718 each time we're increasing. And so this is kind of exponential functions, right? So we have all of these different concepts. We talked about um, the graphs of exponential functions of a to the x, where we had a positive exponent and a negative exponent, what those looked like. We talked about the e. We talked about now our using that e in a function e to the x. And from here, we'll take what we know and apply it to something called logarithms. So that will be our next section. We'll be kind of looking at the converse side and how exponents and logarithms work hand in hand. I look forward to